Hi, this is Willie Harris, and I'm presenting 5 lectures under the series Phosphorus in Agricultural Watershed Science and Application. My lectures are under Module 2, the general topic of how Florida soils interact with phosphorus. And this is Lecture 2. Lecture 2 is the first in a series of 2 lectures on phosphorus dynamics as related to soil morphology and composition. The learning objectives for Lecture 2 are to convey knowledge of morphological cues to processes affecting distribution of soil components, to use that knowledge to focus in specifically on phosphorus retaining components and their distributions. And a third objective is to understand the value and limitations of soil taxonomy in predicting phosphorus loss risk. Here's the outline of the lecture. I want to make a case for the interpretive power of soil morphology, beginning with morphological clues to components controlling phosphorus retention. Then I'll address the distribution of components and their role in P retention for well-drained and poorly drained sandy and loamy soil horizons. I'll discuss the relevance of soil taxonomy to phosphorus retention and summarize at the end with a few take-home points and provide references. Two morphological clues to components that foster phosphorus retention in Florida soils are the presence of sand grain coatings and the presence of loamy layers, also known as argillic horizons or BT horizons. Remember, T is a subordinate distinction that indicates the alluvial accumulation of clay, or the accumulation via translocation from above. The main morphological indicator for the presence of coatings is color. Coatings tend to impart brownish, brighter colors to the soil, whereas clean grains tend to impart white to light gray colors. Morphological indicator for the presence of a loamy layer is primarily texture, as you would determine from consistence. That is, if you have more clay, then, which would be the case for an argillic horizon, you would have a consistence that's marked by plasticity and stickiness. And so we're using consistence as an assessment of soil texture. We will explain some more about these things in the succeeding slides. I introduced sand grain coatings with these images in Lecture 1. I mentioned that these coatings impart some phosphorus retention, whereas clean quartz sands, such as typical V horizons of spodosols like the one you see here, have practically no phosphorus retention capacity. Right now you're probably asking yourself, what are the components in sand grain coatings that have an affinity for phosphorus? This is my take on the nature of sand grain coatings for sandy coastal plain soils of the southeastern United States. They're patchy. They comprise about 2 to 8% of the sandy soil mass. They contain similar proportions generally of silt and clay. The silt is mostly quartz, and the clay consists of quartz phyllosilicates like hydroxylayered layered vermiculite and kaolinite, and oxides of aluminum and iron. Therefore, they're not simply iron oxide coatings as is commonly the conception, but aluminum and iron oxides are very important because they are the coating components with the most tenacious phosphorus sorption, and they serve as a cement to hold the other components on the grains And if they're destabilized, the other components are destabilized and mobilized as well. Hence, they're responsible for not only phosphorus adsorption, a good portion of it, but also moisture retention too, because the fact that they are keeping finer materials within the sandy matrix. The second morphological clue I mentioned to components controlling phosphorus retention was the presence of BT horizons. Here's a soil with a BT horizon, and ultisol. Other orders can have BTs as well. And we see pictured the BT deeper in the profile. The BT horizon can have appreciable phosphorus retention because of the components it contains, and the elevated clay content, which increases the surface area and potential for surface reactions of phosphorus. Here's a soil, an entisol in this case, that has no BT within 2 meters, but many entisols of Florida can have BTs that occur at greater depths. And in both cases, the EA or BW horizon of these soils could have coatings which again could enhance the phosphorus retention capacity of the soil. I have a cryptic comment that this clue is most pertinent for relatively well-drained sandy soils. And so rhetorically I ask why, and even though I will go into this in greater depth in a future lecture, the obvious reason would be that if you have very poorly drained or poorly drained conditions where the water table is close to the surface and you have limited water storage, the risk of phosphorus runoff by surface or shallow base flow is increased, and the opportunity for phosphorus to interact with the deeper horizons in the soil is reduced. So for poorly drained soils, we're looking for other kinds of conditions rather than focusing so much on the components of the horizons deeper in the profile. Sticking with the BT horizon clue, there's something interesting about the sandy soils that occur in the coastal plain of the southeastern United States. No matter how deep the BT boundary, the clay mineralogy changes there. So how does the distribution of components vary among well-drained sandy and loamy horizons? Well, here is the same ultisol profile I presented a couple of slides back, relatively well-drained, with an AP, an E, and a BT horizon. So if we look at the sandy part of that profile, the AP and the E, it is going to have a sand texture with greater than 90% sand. Typically an AP horizon would have organic matter less than 3%. The sand is greater than 90% quartz mineralogically. The silt is greater than 90% quartz. And the clay can contain quartz, hydroxylayered vermiculite, kaolinite, and metal oxides, aluminum and iron oxides. The clay and silt in this zone is mainly in the form of coatings, and it's similar for ultisols and entisols. But if we look below the BT boundary, we have a loamy texture, generally less than 90% sand. Again, the sand is more than 90% quartz, and the same for the silt. But the clay fraction is slightly different. The clay fraction is commonly dominated in relatively well-drained soils with BT horizons by kaolinite. It also has hydroxylayered vermiculite, quartz, and metal oxides. If we look at the phosphorus retaining components, primarily that would be in the sandy part of the soil, hydroxy and layered vermiculite, kaolinite, and aluminum and iron oxides. And in the BT part of the soil, the loamy part, it would be kaolinite, hydroxy and layered vermiculite, and metal oxides. The only difference there is kind of a switch between kaolinite and hydroxy and layered vermiculite, with kaolinite being more dominant in the BT. In the case of comparison for metal oxides versus the phyllosilicates, namely hydroxy and layered vermiculite and kaolinite, metal oxides are by far the most tenacious binder of phosphorus. But with increasing concentration, kaolinite and hydroxy and layered vermiculite would also serve to retain some phosphorus. The distribution of components in commonly occurring poorly drained sandy soils of Florida is a little more complicated than is the case for better drained soils. Here is an example of a poorly drained soil, a spodosol that has an AP, an E, a BH, an E prime, and a BTG horizon. The prime is used in cases where the same horizon is separated in a profile by another horizon. In this case, the two E's are separated by the BH. Looking at the AP and E zone of this soil, we have a sand texture. We have an AP horizon with organic matter content that's not all that high, commonly less than about 3%. The sand is greater than 90% quartz mineralogically. The silt is greater than 90% quartz, and even the clay is dominated by quartz. The clay plus silt content is generally very low in this zone. Looking at the next two layers, the BH and the E prime, again, we have sand texture, and we have the BH horizon with organic matter complex with aluminum, and the organic carbon content of the BH is roughly comparable in many cases to the A horizon. Again, the sand is more than 90% quartz, the silt more than 90% quartz. The clay also can be dominated by quartz, but it does have appreciable phyllosilicate content, hydroxy and layered vermiculite and kaolinite, for example, along with aluminum and iron oxides. And there is some clay and silt, and that material occurs mainly in coatings within this zone. Moving down to the BTG, has a more clay, a loamy texture with less than 90% sand. Again, though, the sand and silt are dominated mineralogically by quartz. But the clay has a little higher proportion of phyllosilicates, such as kaolinite and hydroxy and layered vermiculite, along with quartz and again aluminum and iron oxides. If we focus on the P retaining components, we see that there are P retaining components in the BH and E prime and in the BTG, but there are none in the AP and E horizon of this soil. The question we might ask is, what is the likelihood that phosphorus is going to come in contact with the P retaining components in this soil? And I would say that during periods of high water table, the likelihood is minimal, and that the phosphorus is going to be able to move fairly readily through the AP and E horizons, possibly laterally into streams via surface or shallow subsurface runoff. And hence, even though this soil does with depth have phosphorus retaining components, the benefit that would be derived from them as far as phosphorus attenuation is minimized by the drainage conditions. Pictured here are the 6 soil orders that I introduced in the first lecture. These 6 are the most extensively occurring of the 8 soil orders that occur in Florida. I would like to expand a little bit upon the relevance of soil orders with respect to what you can infer about soil phosphorus retention. The range of properties within soil orders affecting phosphorus dynamics are too wide to safely infer about phosphorus loss risk for entosols, ultisols, and alphasols. They are narrow enough to signal problems for spodosols, histosols, and mollisols. That is because these three soil orders are associated with wetness in Florida. They're wet enough to be mostly poorly drained, or very poorly drained, and by virtue of that, there's a high risk of runoff due to limited water storage in the soil, and phosphorus runoff risk are high in areas where these soils are prevalent. Suborders provide a better distinction than orders, and I'll elaborate upon that in the next couple of slides. To help in communicating taxonomic relevance to phosphorus retention, I'm going to present a brief nomenclature primer. The USDA soil taxonomic system uses formative elements, or syllables that in combination designate classes. These are the formative elements for Florida soil orders. For example, alphasols is ALF, entosols is ENT, histosols IST, and so forth. These formative elements are put together in categories within the system, so when we go from order to suborder, we combine the order classification, for example ALF, with a suborder formative element, like in the top case AQUALF, AQU, aqua. So an AQUALF is a soil that would generally be poorly drained, relatively wet, the aqua being the formative element that conveys that, has that connotation. Sament is an entosol, the ENT part, and the sam means that it's very sandy. And udalt is an ultisol, the ULT part, and the ud conveys the idea that the soil occurs in a humid moisture regime, but that is not as wet as a soil that would have an aqua suborder formative element. There's some other formative elements for suborders that are used in Florida. In fact, there are quite a few that are in this box, examples. I've already mentioned aqua for aquic and sam for very sandy. Then there's flu for evidence of flooding, fibra, hem, and sapra for low, intermediate, and high degrees of organic matter decomposition. Ud for humid moisture regime or humid climate, but the soil is not too wet, otherwise it would probably meet the aqua criteria for poorly drained. And ortha or orth meaning nothing extreme or distinctive. Florida's suborders can sometimes provide fairly useful clues regarding phosphorus loss risk from soils. The relative risk of phosphorus loss, assuming no significant previous loading, would be high for soils with aquic subgroups, aquads, or wet spodosols, aqualts, wet ultisols, aquint, wet entosols, and so forth. And they're high because of wetness, because of high runoff risk and minimal contact with P retentive components, which I mentioned a couple of slides back. Udalts and udalts would be an example of relatively low risk because they have BT horizons that have slightly lower conductivity with longer contact time for phosphorus in solution and relatively abundant P retentive components in the BT. And cements can be intermediate to high risk. They're sandy, and that's probably their main liability. They're highly conductive, and they have a high leaching risk or a high risk of water moving quickly through the soils since they're relatively well-drained sandy materials. The P retention is related to the abundance of amorphous iron and aluminum in sand grain coatings. So coatings are important in keeping it in the intermediate rather than the high range of leaching risk for phosphorus. I put in here the qualification that we're assuming no significant previous P loading, because even a soil that's relatively retentive of P has a limit to how much it can retain before it can become a source of phosphorus itself. There's no sustainable one-way street. Eventually you have to close the loop. My take-home points for this lecture are that color cues the presence of sand grain coatings. Metal oxide cement of grain coatings retain phosphorus tenaciously, and clean grains don't retain phosphorus at all because they consist of quartz surfaces which don't have an affinity for phosphorus. Loamy textures cue the presence of BT horizons, and since BT horizons have clay-sized minerals that can retain P by virtue of the nature of their surfaces and higher surface area. Florida soil suborders can be roughly grouped according to the risk of P loss.